Hey class, good morning. Hey, we're looking at sections in the tutorial today on sections 4 in the textbook. So, right, we're just exposing you to this Python tutorial. This is not meant for you to be an expert in Python by the time you get done with this. Okay, we're just trying to expose you to what the syntax looks like and get you rolling. So you know enough, since you've programmed before, you get the idea what an if statement is, right? An if statement allows you to change the direction of the code, right? You ask, hey, if this is true, then do this code. And then you're allowed to group ifs together, right? So in the case here, in section 4.1, you're allowed to group it. So if this is true, we do this. And all these else ifs and elses are optional, right? They're all optional. So sometimes you can just have one if all by itself. And the code looks like if condition. And the idea is if it evaluates true. So if it evaluates true, then I'm going to do all the stuff between this colon and that continued indentation. And remember, with Python, it uses indentation for controlling the structure. So other languages might use curly braces like Java and C, and Python would use curly braces. Python uses indentation. Then the else if, they shrunk the code, you're losing the LSE and the space. Now, this is only going to get evaluated if this was false. So if this is false, it skips over all those indented lines and it jumps down to the next control structure. And then it evaluates, okay, is it 0? If that's false, then it does the next one. And if this falls, if this is, so if all these conditions are false that are above, then it's going to print more and then continue on with the code. So if drops straight down through the code, evaluates, and it's what's called a branching type of operation. It allows you to split, but it's going to keep going. If you looked at your code like straight up and down, it's going from the top of the page to the bottom of the page. Loops are different. You know, it's interesting here. They went from if to for, but they didn't show you the while loop. So a couple of you guys have already, right, here's the, well, here's a, it says while, but they have a while loop as well. And that's typically what we use. I think I've got it over here. Yep. So this is a little bit more intuitive than what's shown in the tutorial. The tutorial is showing you some of the structures that they put inside Python because other languages didn't. Anyway, they do something called an iterator, and they have lists. And we saw last time with the range operator, which what typically they do, they use a for loop as an iterator. So it goes over a sequence of things. And so Python, I'm jumping my terms here. I'm going to come back to this. Well, we'll come back to that for loop iterator since I've already got this code highlighted here. So we've got our while loop here. This is our, you know, what kind of loops that you're used to seeing in other languages. So while theta is less than or equal to 90. So that means somewhere before theta had to be defined. So let's go look through our code. Yep, okay, so up here theta was 0. And then while theta is less than or equal to 90. So this is different than the program that you guys were doing for the arc length, right? I showed you, we did this arc length program for class. Now I've got my arc, you know, my radius was 0, but let's, anyway, now we're going to do arc length. Sorry, not arc length, X versus Y. So while theta is less than 90, it's going to plot the X, Y, and sine theta. And here we go. And I've got an R of 55. So I'm computing my X and Y components, X and Y. This is something I'm doing for ma305, right? We're just plotting X squared plus Y squared equals R squared in the first quadrant, right? The equation of a circle. I've got a radius of 55. We start out at 0, and we're going to go through 90 degrees, and we're going to plot all the points along the arc in the first quadrant. So I vary theta from 0 to 90, right? So while theta is less than or equal to 90, I compute an X value, a Y value. Here I'm using the NumPy library. So I'm using a couple of NumPy functions, which you should be able to see pretty quickly, right? So theta was in degrees. So originally it was 0 degrees. Then I used the degrees to radians function from the NumPy library, because the sine function, cosine function, tangent function, arctangent function all expect the value to be in radians. So I had to convert the degrees to radians first. I passed in theta at 0 degrees, converted it to radians, and then computed the Y value. And then similarly, X is our cosine theta. So I calculate the cosine of theta first. And then actually when I'm printing it, because I wanted to demonstrate what the sine does and the cosine does, I actually print R cosine theta over here and R sine theta over here, right? I've got the, it's just for the printing. I was kind of hacking something together just to do something for my other class. But, right, so we got theta varies from what? From 0 to 90 degrees. That's this first column, right? Then the cosine of theta, cosine of 0 is 0, cosine of 10 is 0.98, and the cosine evaluates, you know, at 0 degrees, it's a 1. And the cosine is associated with the X value. So each one of these points that we're seeing along this arc is actually, the X value is R cosine theta, and the Y value is the R sine theta. So when theta is 0, the sine of 0 is this next column. The sine of 0 is 0. And then R times the sine of theta is this last column. So 55 times 0, because our radius over here is 55. That's why we get a 0 here. And then since the cosine was 1, we get the X value is 1. So we're plotting the point 55, 0. And then we up it to 10 degrees. So the point here is you can do traditional while loops. We calculate our X value and Y value. And then I'm going to use the old school printing functions. So when you go through the tutorial, I'm going to use this same type of format all semester long. And every time I write a Python code, I'm going to use this type of syntax because I know it from C and I know it from MATLAB, and I don't really want to learn another awkward looking print statement. So this is easy enough for me to make the change, right? I'm used to printing out I have a placeholder for a numeric value. That's theta, right? What kind of numeric value? Well, I got a floating point with 2 decimal places, right? So here's my theta with 2 decimals. And then I throw down a tab key because often I'm going to write this data to a text file, right? So now I'm going to write that information to a text file. And the best way for me, from all my database experiences, tab delimited text files. Commas often lead to problems with like city, state, and zip. You know, you got commas embedded in the data. Not all data is numeric. So my experience is tab delimited data is best. It loads right into Excel, right? Because Excel uses tabs to delimit between what's in cell 1 and cell 2. And it works great for loading data into a database. MySQL loves tab delimited data. In fact, I think their raw MYD data files are actually in tab delimited, or they were way before Oracle bought them, or took it over, or however that worked. So, okay, so we got %.2f tab, %.2f, %.2f tab, ... I don't have a /n because print automatically puts one on there. And then there was options on the print statement, right? If we come, I'm going to skip ahead for a moment and we'll go over here to chapter 7. So we talk about input and output. I'm skipping fancier output and formatted stuff, and I'm just dealing with the old string formatting. So fancier output, right? You're going to do something called formatted output, and then you're putting in these squirrely braces. Say I'm going to put the year in here and the event in there. And so this F tells it to do the replacement for me. So now you're embedding a variable inside single quotes, and then it goes through and figures it out. Or you can use this format option, string.format, which does something similar. So this is saying, you know, put that first value in, and then I've got 9 spaces. It's like using a %s, %9s. So that forces it to have that extra space there. And then you got, you know, 2.2 looks just like what we're doing, right? And this is the second thing. So I just like to use the same type of code. We did pretty much the string example last time. But remember, we can combine strings with numerics, right? So here's our concatenator operator. The plus sign is the concatenator operator. And so if you want to concatenate a string with a numeric, you would put str and then whatever your numeric is. And then we did str and round last time. Again, I'm trying to expose you to stuff. So when you see code, you get it. And here's another format statement, but again, I'm going with old school because you guys have seen it already in MATLAB. Old string formatting, right? You got a string, %values. And then when you have more than one value, you have to put these in parentheses, like I've done multiple times so far. So this is, you know, 7.14 is all we need in 7.1. Reading and writing text files. We'll come back to that. That's not where we are. We were talking about while loops and for loops, but I wanted to show you the printf statement that we'll use predominantly out of section 7.1, that I'm going to use these formatted print statements. And here's the case where there's no comma after the double quotes. So we're going to print everything that's in double quotes to the line. Then we tell it to do a replacement operation. And then we pass it, since there's more than one, we pass it a whole list of things that we're going to replace. And there must be the same number of values over here as there are these formatted spots over here. And here, notice I did a computation, right? I calculated x, which was really the cosine of the value, and y was the sine of the value. And then I calculated the real x, which is r times the cosine and r times the sine. And I did that just so I can do a quick print statement for my other class. All right, then I increment theta. So now back to the loop. Theta originally was 0. While theta is less than or equal to 90, I'm going to do all this code that's associated with it. Goes through, right? So the first time through, theta is 0. It does the calculations at 0. Then it adds 10 at the end. And then I actually plot. I haven't changed. This theta should actually be, theoretically, this should be, I'm going to put this below it. Right? Because I want to plot first, and then I want to alter my loop variable. It doesn't matter here because theta is not associated with the plot command. But I plotted what? I plotted, in this case, I'm plotting a scalar. I'm plotting a blue star for wherever the x position is and the y position is. And again, I'm multiplying x times r because of that little tiny hack to get the x and y values that I really want, but they're not stored in x at this moment and y. So I have to multiply it by x times r to get r cosine theta and r sine theta for my x and y values. Then I add 10 to it, so I was 0 plus 10 is now 10. Back up to the top. Is 10 less than or equal to 90? True. Go back through. So stuff that you guys have learned in other languages is still valid here in Python. And so I just want you to be exposed to this type of while loop, which is probably what you're used to seeing most and probably what you'll use in the future. So some of that stuff in the quick tutorial is written for real Python hacker or programmers, and they do some different things in Python. And Python does a lot of stuff with lists. So quickly we'll see that we'll probably not use all their list functions directly, but the concepts of the list is important to Python. And then we end up using NumPy because NumPy operates on lists faster. If you start getting into the Python machine learning book, you start reading the first few sections of chapter 2, you'll read all about that. Okay, then I threw the plot grid on as true. Plot axis, set axis equal. So this is kind of a complicated code, and we'll talk about matplotlib more, but what this piece of code is it basically makes my aspect ratio the same, right? So 20 units over here, even though they got 10 and 20, but if you measure this, 20 is 20 up there. So our aspect ratio is equal, and then plot show allows me to show my plot. I did, however, in this piece of code, I ran into some warnings that they don't really like this piece of code. Python changes frequently, and now this code is what's called deprecated, and I really did not want to see all the warning messages that come up. So let me actually comment out this code because you're not going to know what I'm talking about. All right, so if I save this and run this, I got to clear all my memory because it's probably still in there because I asked it to deprecate all the warnings, ignore the warnings. All right, now if I rerun, removing all variables. Huh. Well, thanks for, well, on it must be because I'm calling plot differently in arc length over here. Let me change my X value and Y value. What did we have? We had like X was 8 and Y was 5. Well, somehow or other, I've deprecated the warnings, but typically there were a bunch of warnings that I was getting earlier. And the way I've deprecated the warnings or asked it to not show me the warnings is import this library called warnings, and then ignore. It says, hey, if I don't want the, set this signal here, simplifier, ignore the warnings. So it's not going to raise warnings and show warning messages on the screen. Let me see if I can scroll up a minute and show you at a prior time where I was getting, here we go. So I was getting these warnings that MATLAB had changed. I was getting a deprecation warning, adding an access using the same arguments as previously, whatever the warning message is. It didn't like this line of code because I was calling it twice with 2 different plots. Anyway, with the multiple plots, it was yelling at me. It still did the work, but it was yelling a warning message. And so I wanted to suppress the warning message. I Googled around, I found something that said, hey, do this, import warnings, stop warnings, and now they're gone. Okay, so it doesn't change the effectiveness of my code. I just wanted to show it. One more thing here. What were we talking about? We were talking about while loops, and we got a plot. and then while loops. In this case, in your version of the code, I'm gonna run our code again, right? This time we started with some point in the first quadrant. So right now I just hard coded to 8 and 5. Later on, we can use an input function to ask the user for the input, but right now I'm using this code for me. So I'm just gonna hard code it, right? I'm gonna hard code a test case and make sure it works. The trouble though with when you hard code something is you can't hard code the values too many times. You gotta reference what the value, right, in X and Y value, so that you can get back to them. So that when you change X and Y, let's change it to 16 and 35, right? If I change this, hopefully my code still works. So save, run, right? So now I got the points, X is 16, Y is 35, right? And then I'm gonna, now what I asked you guys to do is to step it back down to till X is 0, right? We're plotting this arc length as it's not really falling back to the earth, basically, but we're just kind of like finding, we're gonna hold the R constant and then we're gonna step it back down to the X axis by decreasing Y by 1 each time. Sorry, trying to find the annotate button, mouse, draw, right? So we had our first X point, or first Y, and then the next Y, and the next Y, and the next Y, and the next Y, and we're coming back down. So while, and I do this twice. I do it one way, just plotting the points. We plot the blue stars. So while Y is greater than 0, originally Y was whatever we just hacked or put it in here at, right? We put Y at 35, then it's 34, 33, 32. So while Y is greater than 0, that evaluates true, plot that point, X comma Y with a blue star, decrease the value of Y by 1. And now we're going to compute a new value of X, right? Using the Pythagorean theorem, right? A squared plus B squared equals C squared, right? Well, our R, our radius vector stays the same. So we compute an R. And now our hypotenuse is always going to be whatever this value of R is, right? We had that initial X and Y, right? And we calculated it by using the Pythagorean theorem, right? R squared equals X squared plus Y squared, right? And then we found out what R was. So R equals the NumPy square root. So R equals the square root of all that. And we found R, and we're gonna hold that constant, right? So that distance is always gonna be the same. So it's got our radius of our circle. Now that we know R, now we're gonna step Y down 1, and now we're gonna compute the new value of X, right? So X is increasing as Y decreases, right? The relationship between sine theta and cosine theta. So we decreased Y by 1 in our loop, and then we compute a new X value, and then we go back through. Is Y greater than 0? Yes, plot that point. And then just keep going. And we keep doing this while Y is greater than or equal to 0. So that's plot, 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 plot. That gets us our blue stars. And there's actually a red dot within there. So I did it a second way, just to show you probably I'm gonna call it maybe the better way or another way. So the second version of plots an array. Okay, and then we accumulate that array. In chapter 5, they talk about lists. Python doesn't have a native, Python does not have a native array data type. They use something called a list, and it allows you to put arbitrary types in it. 1 minute you could be putting an integer, then you could be putting a float, and then you could put it in a string. Okay, NumPy is going to force us to do numeric type of array operations, kind of more like a MATLAB would do or a C would do. So this time, right, I've got an OR statement here. I'm just saying, or we could plot it. We could plot it point by point by point, or I'm going to reinitialize my X and Y to what they were originally, because I was modifying X and Y to make that plot. So I reinitialize X and Y, and now the X values are equal to a NumPy array with nothing in it. So NumPy can take a list and turn it into an array. And that's what we're doing with this code here. NumPy array, and I'm passing in a blank list. The list is what goes in between these brackets with comma separated. Well, here I got nothing in it. So I got a blank X array, X values array. I got a blank Y values array. So while Y is greater than or equal to 0, X values equals NumPy append to the X values array, the element X. And now we basically accumulate an array, right? And if we look at our X values at the end of that program, here's all our X values. So at one point, X is 16, right? The very first point. And then at the end, when we drop all the way back down, so the last element of the array, X should be whatever R is. R is 38.48. And so as we come all the way back down, R is 38.48, right? Because it's just the radius. At this point, the sine of theta is 0. All the radius is in the X direction, R cosine theta. And so it's X is increasing as we come back down to the ground. That's why Y is decreasing. So the sine function's decreasing in value, right? Because this is our theta. Our angle here is our theta, right? And the sine of theta is 0 at 0 degrees, and the sine of theta is 1 at 90 degrees. So all the values going toward the Y direction, or sine is associated with our Y. We're talking about this angle here. Okay. So we built that array of values, and then we plotted it. And then I plotted it in red to plot a dot. So I got a dot in the center just showing that inside my blue stars that it worked. Doing the exact same code, I just did a little bit differently. And then I kind of segmented it by throwing these little green lines in there as well, right? So it kind of shows that segmentation. Like if you had a, it's not, the more data points you get, the smoother the curve is basically what we're showing here. So, piecewise linear, and then the more points you get in there, you get a nice smoother curve. Okay, so it makes your plot look better. Depends if you can plot continuous variables or not. Here we're plotting, points or line segments. Okay. That's it for this particular code. Clear all. Back to my mouse. Back to our Python tutorial, right? So we were just talking about lists, data structures, and lists. So lists. So we append an object to a list, which is what we are doing. Extend by appending all the items from an iterable. So we can insert elements, we can remove elements, push elements and pop elements. If if you're from more of a data science people, where you have queues and you're pushing elements, stacks, where you're pushing an element onto a stack and popping an element on a stack. You can remove all items from the list. So we emptied the list. We can return the indexes, count the number of times X appears in the list. So this is kind of cool. You could see if like the number 55 appears in your list. So if list.count 55 is greater than 0, this is the value. This isn't the index element. This is the value, right? Number of times X appears in the list. It's not the index, it's the value. So it's pretty cool. You can sort your values, you can reverse, you can copy it, and then you can play with this code here. I don't think there's anything. The idea is that you have a list, and that what we did with our list in a NumPy, we used an array rather than a list. The syntax looks very much the same. We create the array, and then we append values to the array, which literally creates a brand new array with another element on it, and it overwrites the old one. All right, so there's lists. You can play with those lists. Again, talks about stacks and queues. I'm not trying to explain every concept, what a queue is or what a stack is. These are computer science type concepts. If you're interested, great. If you're not interested, it's not going to affect the scope of this course. We will talk about a Lambda function probably a little bit later, but it's like an inline function. I want to do something right now. And again, I don't really expect you to understand all this code here. I would play a little bit with these lists, mostly in this section here, right? Or just read over this. This is like the most important one, 5.1. All right, list comprehension. That's not that important. Nested, if you want to read about what a list, this is just getting more complicated. And we're not here to get it complicated. I just wanted to expose you to it. Delete allows you to remove an element from a list. Tuples are not important in my world, but here you have a comma separated list without double quotes around it. So it's called an immutable list. Sometimes the only place I could use this is for a dictionary array, which they talk about dictionaries. Sets, we're probably not going to use, but there is a cool function here within, allows you to say, does this, if you had a set of data, does something exist in it? But you could loop over the array and check it too. So I've never used sets. Dictionaries I've used quite a bit. Dictionaries are basically an array. Well, they're using the set syntax. The set syntax uses the squirrely brace. The list syntax uses the square brace. And the dictionary object is using the squirrely brace too. But basically, this is saying map Jack to 4098. Like that's the extension of Jack's phone number. And whoever SAPE is, map her number to 4139. And then we're going to add a dictionary object. Guido just came on board, and we're going to add another telephone number to our dictionary. So telephone is called a dictionary. The index can be a string or a number, and it maps to a value. It's really useful. Like I use it with parcel numbers and mapping whether or not they have a house or not. So it's just a quick way to do an index based off of a text value. So here's the text, here's the value. And I believe you can do the in clause too on this, yes. So you can say, hey, does Guido exist in my telephone dictionary? True. And note that Python's true syntax is a capital T for true and capital or false, or capital F for false. Oh, good. So you don't always have to use the squirrely braces. You can use the array-oriented brace. However, you got to group them in parentheses. Okay, so this maps to this. So there's two ways of building the dictionary. You could use the square brackets, and then each element of the dictionary uses, right? Each element is like an XY point, with parentheses around it. Or you can use the syntax of the squirrely brace and map element to element. So you got element in single quotes because they're string based. colon value, string colon value. Okay, looping techniques. I already showed you the loops that I think are important at the moment. What they're showing is like looping over, well, in this case, we've got what, a dictionary. And this dictionary gives me two things. We've got this guy, the pure. So in this list of the items of this dictionary object, it's going to return two things, the key and the value. And so I'm going to print the key and the value, which is why they called it K and V. So items of my dictionary returns me what's called an iterable object. Then I can throw that to my for loop, and it'll iterate each one of them, pull back the first element here, and then it'll look for a next, and then a next, and then a next. Enumerates is to tell it to put it in a numeric order. So we got tic-tac-toe, 0, 1, 2. Enumerate means to turn it into a numeric, right? The very first, it's a counter. It's going to start at 0, and for as many things that get returned, it'll just add 1 each time. All right. You can reverse the orders. You can sort the orders. We're not going to use too much in math. You might use the not available number. We'll probably get that a couple of times. You might have to test for float not available number. But most of the times we'll use the NumPy library just because we're already going to be importing it anyway. NumPy has a square root function, sine, cosine, tangent, and most of the math stuff we'll use. Okay. All right. So that's section 5. What else we got? We got modules and 6. So modules so here's a user defined module. They're defined in the Fibonacci number, and you're going to pass in n. So when you define your own functions in Python or C or Java, that's what, you're defining your own function. And then modules are stuff, a lot of times when we're importing our modules, we use the import statement, right? So if it was your own code Fibonacci, right, we're going to import star from Fibo, and that means we're going to import all the stuff that they had in fibo.py. And then we use the as to force it. So we're going to call it as fib, or like import numpy as np. We do that so that we don't clobber the namespace with, let's say square roots defined in 2 different places. This forces us to use the numpy.square root, which is like what we did over here in the code, right? I use the numpy.append or plot.plot. I'm using the function plot from the plot library because I imported matplotlib as plot. NumPy, right? We imported NumPy. Anytime we use a NumPy function like square root, we have to bring in that np alias first so that we know that we're using the square root function from the NumPy library. Okay. Executing modules as scripts. This is something we were talking a little bit last time, where we want to run a program from the DOS prompt, call Python and the name of your program, and then here's these command line arguments, right? And then here's so not quite sure what all that code was, but here we're passing in a 50, and so we want to do the Fibonacci series on argv1. Argv0 was my program name. Argv1 was my first value. And so I'm going to run the Fibonacci on converting that data that came in. It came in as a string, the 50 comes in as a string. I have to force that string to an integer, and then I can run that code on, or then then I'll run my Fibonacci code up here, which then does all this work right here. And we had two functions here in fib.py, fibo.py. We got fib, and again, it looks just like a while loop or an if statement where we have everything's indented that goes with this function definition. We start our function definition out with define fib with the arguments that we're passing to it, and then colon, and then it does this operation. In this case, we don't return a value. We're just going to write them to the screen. In the second case, we define a second Fibonacci number. So we got two functions. We got fib, and we pass in that 50, or fib2, and we pass in 50. Here, we're actually doing the work, but we're not returning. What we're returning is the result of the function. So we're probably going to append that whole sequence of values together, and then we're going to, we're appending all the data together, and we're going to append that Fibonacci series, and we're going to return the whole result. In this case, we just printed it. In the second function, we're going to return the result. So you would say, you know, x equals fib2 pass in 50, and now x in your code has that whole Fibonacci sequence. And then you could iterate over that because it was a list, right? We define, here's an empty list, the list, and then we use the append function. We appended A to our result. A little bit different than the way we did it with the NumPy, but that's okay. We're appending to the list. All right, more on modules, executing them as script. Make sure they're in your search path. I'll let you read over the rest of 6 standard modules, right? Importing the system library, using the directory function, other packages that you want to install. We're going to install millions and lots and lots of packages. Importing star is kind of a, it says import everything, but you can import just from sound effects, I want to import everything, or or you can import just a specific module. So it depends on what you want to do. And again, we're here to expose you. So we did 5, 6. The range operator we were talking about last time, and they told us right here, range gave me this iterable type of number. If you want to actually see all the values in the list in the range from 4, it really returns me 0 to 4, but it's an iterable structure, and list allowed me to get to that iterable event. List range 4 returns you that 0, 4, or just 4, and so list allowed it to sequence it out for you. Break statement breaks the nearest enclosing loop, just like in C or Fortran, or not Fortran, like in C or Python or Perl. Continue goes right back up to the top of the loop. Continue goes right, breaks you out of the nearest containing loop. Continue continues back up at the top of the loop and does not evaluate any more of the code below it. It's useful for testing for a condition. Anyway, I've used it a few times, quite a few times. And else I've never used, but like, hey, if something doesn't happen, then else do this. That's an interesting construct I've not seen in other languages. Pass statements like a blank, it's like a semicolon. It really doesn't do anything. Define functions, we just talked about that with the modules. Define our own function. If you want to define your own function, use the define Typically, you put it at the top of the code so you can use it below it. And then here's the Fibonacci. I would probably run these 2 Fibonacci codes and type them in. And then I'm not going to get too far down into the more on functions. When you need to define your own function, it might be worthwhile knowing this information's here to come back and get help. All right, so this is really, and then Lambda, we'll use Lambda again later, but it allows us to run a function internally. I have got to scoot. I've got to take my wife to a couple of appointments this morning, and so I won't be available with you during the class today, but this should get you through sections 5, 6, and 7. And if you got questions, email me. I'll be back around 3 o'clock this afternoon. I'll be in my office. All right. Have a great day, and we'll talk to you soon.